let's look at a data set that has more than just the one predictor that we used in the previous data set. So this comes from a real data set about cancer, and I want to get across that I'm not just using this like, well, we might as well talk about cancer. Like I've had friends and family die of cancer, and this specific cancer in particular. Perhaps you have too, although I hope not. So we should always remember when we're doing STEM work, like the people who were involved in gathering this data set and what they were going through with a lot of it. In this particular data set, researchers took biopsies of cells from tumors, and some of the tumors were maybe dangerous cancer and some were maybe not dangerous. So let's take a look at a sample photo. Where did I put that? These are microscope images of cells from the biopsies. The word benign means not harmful or maybe not dangerous. Malignant means dangerous or harmful or probably going to spread or something. So what researchers would do is look at the microscope image and maybe outline each cell and take measurements like what's the area of the cell, what's the perimeter of the cell, what's the radius of the cell, like from the center to each point along the edge, and then take the average of those to say what the average radius of the cell is. Um, they might say, like, does it have any points of concavity or how many, where it's not just a round blob, it actually comes in and then goes out again. Um, so they would measure that for each cell in the image and then take like the average of all the areas of the cells in this image from this person, or the average of all the perimeters of the cells for this person. Um, and then they also know, based on some other kind of gold standard test, whether the person actually has a malignant cancer or if it's a benign sample. If biomedicine isn't your thing, you can imagine a similar study where we take like cross sections of steel, take microscope images of those, and look at the metal grains, and we want to say whether or not the steel is strong enough for this particular application. So we want to come up with a mathematical system that, given various measurements like radius, texture, perimeter, etc., will attempt to tell us something about benign, malignant or benign. So let's go back and look at that Excel sheet. It's got definitions of things here like radius. Texture would be like how mottled is the gray of the cell. Is it like all the same gray or like some light, some dark? Perimeter area, compactness, like a circle is perfectly compact. So if the squared perimeter divided by the area -1 is 0, I think that means it's a perfect circle. Um, of how concave are portions of it, how symmetric is it. If you were doing an actual study on something like this, you would want to really know the definition of each of these. You don't have to know it for this homework or whatever, but just as a demonstration of the kind of detail-oriented thinking you need. When we say researchers measured, they probably sat there literally with a mouse and drew around the picture of the cell on their screen. Let's take a look at the data we get. So we've got 568 rows, each one representing data from a person. We've got some sort of study ID number. Um, we've got whether that person actually had a malignant tumor or if the tumor was benign. So you can see we start off with a bunch of malignants. Down here we've got some benign. And then what was the mean radius of the cells in nanometers or millimeters or probably more like micrometers. So all kinds of these measurements. So we've got a lot of numbers here. How could we go about exploring how the numbers relate to being malignant or benign? So one way we could do it is pick one measurement, for example, like maybe the area, and then try to make a scatter plot of another measurement with it. So I've chosen compactness here, um, and try to color the dots differently for malignant or benign things. So that's actually kind of hard to do in Excel. I've got a table set up here. You don't need to do this for the homework, but it's a nice Excel skill to know. Here we're just saying copy the area. And then in this cell, we're saying if the diagnosis here matches the diagnosis label up here, which it doesn't in this case, then give me the value from column I, otherwise give me a NA, not applicable. But over here on this row, it is a malignant diagnosis, and so that does match, and so it gives us the value from column I. So each row should have a not applicable in one of these two cells and an actual number from column I in the other one. And so when we plot that, we get this, and I've made it clear that like the malignant cells are a different color and a different shape of marker, just in case this gets printed in grayscale or something. So the question is, can we come up with a mathematical system to say, based on the area and the compactness, are we going to diagnose this as malignant or benign? So think about how you might do that for a minute. We might be thinking, well, I could draw maybe a line, and anything on one side of the line I will say is malignant, and anything on the other side I say, well, I'll say is benign. So you could kind of eyeball a line through here that, most of the dots above it are malignant, most of the dots below it are benign. It wouldn't be perfect. We'd have some false positives and false negatives, and you got to expect that. And it's our job to kind of measure those and quantify them and such. So how would we mathematically draw a line? Well, I've got an example up here. We could say a line is like y equals mx plus b, right? Unfortunately, m and b for slope and intercept sound like m for malignant and b for benign, but it's totally separate here. And so I've just typed in an m and a b. I've plotted 2 points here and plotted them on a scatter plot. There we go. And I could change my slope and intercept. Let's bring it up where we can see it. So if I use a slightly steeper slope, how about negative 0.00009, you can see that this line became more negatively steep. Or I could do 15 and make it even more steep. So I would hopefully adjust those parameters to get a good balance of false positives and false negatives, for example. Now this is a hard classifier. We're saying if it's above the line at all, call it malignant, rather than saying like 90% malignant, or I'm 90% sure it's malignant. So we can talk about that later. But let's also think about what we're saying here. If we're saying if the y value of the point is above the line, mx plus b, then the point is, then we'll say the test result will be malignant, otherwise benign. Or we could say, instead of y and m and x, we could say if the compactness, that's the y-axis, is above m times the area plus b, we can do algebra to move stuff from one side of the equation to the other by subtracting. So we get if compactness plus negative m times area plus negative b is greater than 0, then the point is above the line, say malignant. Here, compactness doesn't have a coefficient on it, but area does. We'd like to treat them kind of similarly. So we could put a coefficient on the compactness. We can multiply by 1. That won't change anything. So that says if 1 times compactness plus negative m times mean plus negative b is greater than 0, then say that the point is malignant. That means the thing on the left side of the inequality here is kind of like a score. If the score is bigger than 0, we'll say that the data point is malignant. Otherwise, we'll say that it's benign. So that is the essence of what we're going to be doing. We're going to say, give me some multiplier to multiply by some predictor, and another multiplier to multiply by another predictor, plus maybe we would have 3 or 4 or 10 or a million predictors, and then add a bias term. And that's our score or our logit. And then we could put that through a logistic regression curve. We're not saying we would, to make a more soft classifier and then use that cross entropy loss. So don't worry about it, but if you're curious, we can talk about it. So we would then like adjust the M and the B, the M1, the M2, the B, to make this dividing line more steep or less steep. But then we could also say, well, can we make the logistic regression more steep or less steep? So that's extra complicated, and we can talk about it later. By the way, the original data set had all these things, but then it also had like basically the standard deviation of the radius and the area and stuff, and then also the largest of the radius and the largest of the perimeter and so forth. So that brings us to like 30 predictors. It's not hard to handle in Python. I wouldn't want to do it in Excel. And so we're just focusing on the 10 predictor case here. Um, so we'll do a more Python approach to it in a later video.